Hello, Honors Algebra 2. Today we're going to talk about the Edgenuity section 9.6 called Properties of Logarithms. Our objective for this section is to evaluate, expand, and simplify logarithmic expressions using properties of logarithms. So let's get a look at our first problem. We want to write this expression here as a single logarithm with a coefficient of 1, meaning it'll start out with log something. So let's take a look at how we read this, make sure we know how to read it. Log base 3 of 6c plus log base 3 of 1 over 12. And all we're going to do is look at how we might condense this, okay? So here's the rule. As long as you've got the same base, you can put addition together, you can condense it into multiplication. So this will condense into a single log base 3 of, and addition condenses into multiplication. So this will be 6c times 1/12, which is log base 3 of, and when you multiply not a fraction by a fraction, you multiply to the top only. So this is log base 3 of 6c over 12, because 6c times 1 is just 6c. And then if I focus on 6 over 12, I can reduce that by 6 to 1/2. And so I get 1 times c is c over 2. And so I get log base 3 of c over 2, or maybe I put parentheses around it to make it a little more obvious that I'm keeping all of that together. The parentheses aren't necessary, but sometimes are helpful to just clarify that you're grouping it all together with the logarithm. I'll give you a moment to look at that. And let's move on to the next question. All right. So let's suppose that we're given this fact here. Log base 7 of 2 is approximately 0.356. And let's say we want to evaluate log base 7 of 98. So let's explore 98 for a moment. I'm going to do a factor tree on it. I know it divides by 2, and 2 times 49 is 98. And 49 is actually 7 times 7, 7 squared. Now, that is really going to help us, and I'll show you exactly how. So what we're going to do is we're going to call log base 7 of 98, we are going to call that log base 7 of 2 times 49. Okay? And just like addition condenses into multiplication, multiplication expands into addition. So this is like log base 7 of 2 plus log base 7 of 49. So that's helpful. Now, we're given an approximation for that, so this is approximately 0.356 plus. Now, let's talk about this one, okay? 49 is 7 squared, right? And let's talk about how you would do log base 7 of 7 squared. Supposing that I set it equal to x and rewrite it in exponent form, okay? So that would be 7 raised to this power has to equal this answer, right? So 7 squared. Well, the bases are the same, so x just equals 2. So the answer to this is that exponent right there. And you can probably see from the way I did that work that this is the way it would work every time, right? If you've got log of something, log base something of that same thing raised to any power, then that power is just going to be the answer, right? So this is 0.356 plus 2, which is 2.356, and there's our approximate answer for log base 7 of 98. I'll give you a moment to look at that. And let's look at the next question. We want to write this big long expression here as a single logarithm with coefficient 1 again, or in other words, we want to condense this, okay? Now, subtraction, and we're going to talk about why in a later problem, in a proof actually, but subtraction condenses into division. And what I'm going to do is I'm going to focus on these two first. So I've got log base 9 of 10 minus log base 9 of 1/2, and I'm going to think about those together for right now, minus log base 9 of 4. So thinking of just these two first will help me do the condensing correctly. If I try and think of things in terms of 3 subtraction problems, it's not very helpful, or 2 subtraction problems. I need to think about 1 subtraction problem at a time, 1 addition problem at a time, so on and so forth. Because all of those operations are what we call binary operations. In other words, you can only do 2 of them. You can only put an expression with 2 things together at a time. In other words, you can only do these operations 1 at a time. You can't do 2 subtraction problems together. You have to do 1 subtraction problem, get the answer for it, and then do the next subtraction problem. So that's what I'm focused on here. So subtraction condenses into division in the same way that addition condenses into multiplication. So this becomes log base 9 of 10 divided by 1/2, and we'll deal with cleaning that up in a second, minus log base 9 of 4. Now, division, particularly that division right there, is multiplication by reciprocal. So this is going to be, I could think of this as log base 9 of 10 times the reciprocal of 1/2, which is 2, minus log base 9 of 4. So then this is log base 9 of 20 minus log base 9 of 4, and this again condenses into division. So it's log base 9 of 20 divided by 4, which is log base 9 of 20 divided by 4, which is 9, or which is 5, sorry. So log base 9 of 5 is our condensed answer. I'll give you a moment to look at that. And let's move on to the next problem. All right, so let's evaluate something a little more abstract. Log base 3 of a over 3. If we're told that log base 3 of a equals negative 0.631. So let's look at this log base 3 of a over 3. And the key to this is going to be, I could think of this two ways. Maybe I'll do it both ways. Excuse me. I could see that it's division here and say division expands into subtraction. So I could think of this as log base 3 of a minus log base 3 of 3, or if you like 3 to the first, but that's not really necessary. So we've got log base 3, whoops, instead of putting log base 3 of a again, let me put what log base 3 of a is. It's negative 0.631 minus, let's talk about log base 3 of 3, or if you like 3 to the first. Let's set that equal to some variable x, and rewrite it in exponent form. That is 3 to the x, that base of 3 raised to the x equals this, and then I can ignore the bases and I get x equals 1. So log base 3 of 3 equals 1. So I'm doing negative 0.631 minus 1, or plus negative 1, which is negative 1.631. And so there's my answer. That's one way of doing it. There is a second way of doing it. And the second way is a little more clever, I would say. Let's say log base 3 of a over 3 is the same as a times 1/3. And this is actually going to show you a clever trick from a proof later on that we're going to come back to. So then multiplication expands into addition. So we have log base 3 of a plus log base 3 of 1/3. And I can do some more side work here. So there's one thing of side work. Here's another thing of side work. Let's explore log base 3 of 1/3. Let's set that equal to some, actually let me set it equal to some y instead, so that I'm using a different variable this time. That's a base of 3 raised to the answer equals this, and then 1/3 is like saying 3 to the negative 1 power. So then I can ignore the bases, and y equals negative 1. So that means log base 3 of 1/3 equals negative 1. So again, I get negative 0.631 plus negative 1. And of course, that gives me negative 1.631 as my answer again. Of course, I'm going to get the same answer. All right. That was cool. I'll give you a moment to look at that, see if there are any questions. All right, there being no questions, let's move on. Now, this one, we want to rewrite 3 times log base 5 of u times v to the second over w to the third as a single log with coefficient of 1. So in other words, we're just trying to get rid of this part. And we're going to use a logarithm property that simply says this, okay? If I've got x times log base b of a, that is equal to log base b of a to the x power. And of course, you can go backwards. You can put it on the outside too. So when I'm looking at 3 log base 5 of uv squared over w cubed. All I have to do is make this an exponent of the whole thing. So that's log base 5 of uv squared over w cubed raised to the third power. Now, technically I'm done, but there is more simplifying that I can do. And the other simplifying is to use the rule that when I have a fraction raised to a power, that power goes to everything in the fraction. So this is like saying log base 5 of u to the third times v squared to the third over w cubed to the third. And then you can just use a property that when you raise powers, two powers, you multiply the powers. And you say log base 5 of u to the third times, that would be v to the 2 times 3, or 6, over w to the 3 times 3, or 9. And there we have the most condensed, simplified form with coefficient 1. I'll give you a moment to look at that. All right, let's move on to the next problem. We want to evaluate this given the fact that log base 12 of y equals 16. So I'm going to use the rule that I just used in the last problem, but I'm going to use it backwards. I'm going to take that power and put it out front. So the rule is that if you have something that looks like this, you can take this and put it out to the front. So this is like saying 2 times log base 12 of y, and then I can use that handy piece of information and say this is 2 times 16, because this is 16, and 2 times 16 is 32, so I get an answer of 32. I'll give you a moment, let you look at that. And let's move on to our next problem. Now we want to simplify as much as possible, that is to condense all of this as much as we can, know as much as we can about it. So there's a lot of things involved here, right? There's some things to notice. This can be written as a power of 2. This can be written as a power of 2. So I can write this as 3 times log base 2 of 2 cubed plus 4 times log base 2 of 2 to the negative 1 is how you write 1/2 as a power of 2, minus log base 3 of 2. So there are two ways of doing these. You could either bring these out to the front for both exponents and do the multiplication that way, or you could just say, okay, well, log base 2 of 2 to the third, that answer is that answer is that, and do it that way. I'm going to do it that way. Well, now let me do it the longer way just so you can see. But it would be log, or 3 times, and then if I put this out in front, that's another 3 times log base 2 of 2 plus 4 times negative 1 times log base 2 of 2 minus log base 3 of 2. Notice that this one has a different base, so there's not much that we can do about it except for just tack it onto the end of everything for right now. So this would be 9 times log base 2 of 2 is 1, plus 4 times negative 1 is negative 4, times log base 2 of 2 is 1, minus log base 3 of 2. And then we've got 9 times 1 is 9, negative 4 times 1 is negative 4, minus log base 3 of 2 equals 9 plus negative 5, or negative 4 is 5, minus log base 3 of 2. And that's really as simplified as we can get. I suppose we could try and write 5 as a log, but that really isn't simplifying. That's sort of complicating things even more. So there we have it, 5 minus log base 3 of 2. I'll give you a moment to look at that. And let's look at the next problem. Now we want to expand this involved logarithm that involves a more complicated fraction. Okay? So the way I want to do this is I want to break it apart and look at everything separately. Okay? So this is like log base 20 of, and what I want to do is I want to look at m over n to the 5th times p, and I want to break it into its individual parts. It's m times 1 over n to the 5th times 1 over p. That's like expanding it out quite a ways. And so that's how I want to look at it here, as m times 1 over n to the 5th times 1 over p. Okay? So that's some side work there. And then all these multiplications expand into addition. So this is log base 20 of m plus log base 20 of 1 over n to the 5th is the same as n to the negative 5th, right? The reciprocal of n to the 5th. Plus log base 20 of 1 over p is p to the negative 1 power. So then I can move those exponents out to the front and have log base 20 of m plus negative 5 times log base 20 of n plus negative 1 times log base 20 of p. So that's why I wrote this as this and this as this, so that I could pull off that little trick. And then I can turn the plus negatives into minuses to make it look a little simpler. But this would be, in my opinion, a perfectly acceptable answer. But I can change the plus negatives into minuses, and then 1 times stuff is just that stuff, so I don't need the 1 there. And there we have the expanded version as simplified as we can get it. I'll pause for a moment, let you get a look at that. And let's move on to the next problem. All right, let's condense this. Now this one's going to take a little more work because of this, okay? How do we deal with that? Well, let's look at some side work here. Let's suppose that log of s, the common log, that is log base 10, equals x. Then that would be base 10, 10 to the x, equals s. And I could do something clever here. Notice that I've got log base r in the problem. So what if I did log base r of each of these things? Log base r of 10 to the x, log base r of x. And then let me use that exponent rule to move that x out to the front. So x times log base r of 10 equals log base r of s. And notice that this equals x. So let me solve for x by dividing by log base r of 10 and dividing by log base r of 10. So then x equals log base r of s over log base r of 10. So I can do that. One little more interesting thing that I could do is the same thing to the common log of r. Let me set that equal to y. And then this would be x over y. Okay, and I'll rewrite it that way. So I've got x over y times 8 log base r of s minus 3 log base r of t. And I'm going to do the same thing here. 10 to the y equals r, and then log base r of 10 to the y equals log base r of r. But log base r of r is going to be 1, right? So this is going to be y times log base r of 10 equals 1. Then I'll divide by log base r of 10 and divide by log base r of 10 and get that y equals 1 over log base r of 10, right? So now I have my x over y that I can write, okay, in terms of log base r. This is log base r of s over log base r of 10 over 1 over log base r of 10. And we'll clean that up here in a minute, but I am going to focus on doing some stuff with this. I can make those exponents. So log base r of s to the 8th minus log base r of t to the 3rd, and then I can condense this subtraction into division, and I can turn this division into multiplication by reciprocal. So log base r of s over log base r of 10 times, not 1 over, the reciprocal of 1 over log base r of 10, which is just log base r of 10, plus, and then I can condense this into division, so that'll be log base r of s to the 8th over t to the third. These log base r of 10s will cancel, and so I've got log base r of s to the first plus all of that, which condenses this addition, will condense into multiplication. So that's going to give me a log base r of s times s to the 8th is s to the 9th over t to the 3rd. And there is my condensed version. I'll give you a moment to look at that. A lot going on in this problem. Just got to take it one little bit at a time. This is by far the trickiest part of that problem, right? All right, let's look at another one. Now we're going to move into some proofs. So let's prove that division expands into subtraction, that subtraction condenses into division. So here's how we're going to do that. I'm going to use the trick of rewriting x over y as x times 1 over y. Okay, so log base b of x over y equals log base b of x times 1 over y, which equals log base b of x times 1 over y is the same as y to the negative first power, which equals log base b of, now I can use the property that I can expand multiplication into addition, so log base b of x plus log base b of y to the negative first. And then I can use the property that I can use the exponent property there. So log base b of x plus negative 1 times log base b of y. And then finally, that's log base b of x, and 1 times all this is just all that, so plus negative log base b of y, and then turn plus negative into minus. Log base b of x minus log base b of y. And there we have it. Q, E, D. Thus, it is proved. Quod errata demonstratum. I'll give you a moment to look at that. That is a proof. So keep that in mind. And let's do one more proof. Let's prove this relationship here. Okay? So let's look at, in particular, let's look at this. Okay? So log base b of, now b to the x plus y is the same as saying b to the x times b to the y, right? And now I have multiplication that I can expand into addition. So that's log base b of b to the x times log base b of, or times, not times, plus log base b of b to the y. And I could either use the property that I can bring them out to the front, or that log base b of b to the x, log base b of any b to the anything, if I set it to some arbitrary variable and rewrite this in exponent form, that it has to equal the exponent. So this is x, and this is y. And there we have it, quod erat demonstratum. All right, so I'll give you a chance to look at that. And thank you for following along today. That is the end of the lesson.